closest dessert costs. So for this problem, we are giving a base cost, and we are also giving the topping cost and the target. So let me first explain the problem. So we are giving the base cost. So this means for each of the time, if we want to make our ice cream, we have to choose one of the base. So for example, we can choose a base 1, so it's gonna have a cost of 1. Or we can choose a cost of the base which is gonna be 7. So that is our choice. Yeah, we have two different choices. But we cannot choose two at one time. So for making an ice cream, basically we can choose one base. But how many toppings we can choose? We can choose for each of the toppings. So for example, this is a topping cost 3. So for this kind of a topping cost 3, we have 3 different choices. So the first choice is we will not choose any topping, so it's going to be a 0. And then maybe we're going to choose one topping of this type, so it's going to be 3. Or maybe we're going to choose 2 toppings of the same type, so it's going to be a 6. Yeah, so 3 times 2, it's going to be 6. So this is just according to the definition. So the base cost, so it is an integer. And the topping cost, it's going to be, yeah, it's going to also be integer as well. And also we are giving the target. So let's just check here. So there must be exactly one ice cream base. So this means the base must be 1. We must choose one of them. Yeah. And here, you can add one or more types of toppings or have no toppings at all. Yeah. But there are at most 2 of each type of topping. So what does this mean? So this means we can choose 3 or 3 and 4. Yeah, for this example. So this is our toppings, 3 and 4. So this means we can choose nothing. 0, it means nothing. Or we can choose a 3. That is also okay. Or we can choose 2, 3. It's going to be 6. Or we can choose 4. That is also okay. Or we can choose 8. It means 2, 4. Or we can choose 3 and 4. Yeah. It's going to be 7. Or we can choose 2, 3 and 1, 4. Definitely it's going to be 10. So this means there are going to be different kind of cases, but we must meet the condition. Yeah. So we can also turn this problem into a 0-1 knapsack problem. Because the condition is limited, but for each of the type, we're going to have a condition. It's going to be less than or equal to 2. It can be 0, or it can be 1, or it can be 2. And also for this 4, it can be 0, 1, or 2. We just need to find how many different combinations. So now, maybe we're going to turn this array. So this is a 1D array. We're going to expand this 1D array. And we're going to find how many different kind of cases. So maybe this is a 0, and here going to be 3, and here going to be 6. And for this 4, if we didn't choose it, it's going to be 0. Yeah. Or we're going to have a 4, and maybe we're going to choose 2, 4. It's going to be 8. Yeah. And then this is going to be the very simple case of 0-1 knapsack. And for this array, we just need to decide which one to choose. Or we're going to have a 0, or we can have a result of 3, or we can have a result of 3 plus 4, 7, or we can have a result of but this is not easy to understand the problem. Let me just explain it like this one. Yeah, still we're gonna have 3 and 4. Yeah, but just for each of the type, we're gonna have a limitation of 0 and 1, 2. And also for this 4, we're gonna have a limitation of 0, 1, and 2. We just need to combine all the different cases. Or maybe we can choose 2, 3, and 1, 4. This is okay. So it's going to be 6 plus 4. So it's going to be 10. Or maybe we can choose a 1, 3, and 2, 4. This is also okay. Yeah. So the result is going to be 3 plus 8 is going to be 11. So this is 10. Yeah. We just need to check how many different kind of cases and which one going to be the closest to the target. Yeah. So the target is going to be 10. So if we have a value of 9 and 11, both of them are close to target, and they are equal because 9 minus the target, the absolute value is going to be 1. 11 minus the target, 10, the absolute value is going to be 1 as well. But we're going to choose the smallest, and it's going to be 9. Yeah, so this is our return. So if there are multiple cases, we're gonna return the lower one. Yeah. Now let's just start the coding. So we're gonna use the brute force. Let me prepare a self.result as my global variable, and then I'm gonna check all the base. So for base in base costs, so I'm gonna call a DFS. I'm gonna start it from the index 0. So this index is basically for the topping costs, and I'm gonna use this base. So I'm gonna call all the functions for each of the base costs. So this means for the brute force, I'm gonna choose a base of ice cream, and then I'm gonna try to find how many different kind of toppings. So this is gonna be a brute force. But if we want to easily understand the problem, it's gonna be a 0-1 knapsack problem. Yeah. So after call the DFS, definitely we're gonna return the final result. Now we can simply write the DFS function. So inside it's gonna be an index and the cost. So this cost is just from the beginning, so this cost is for the base cost. Yeah. So the condition is that if I equal to the length of the topping costs, so we're gonna do some calculations. Yeah. So the calculations from here is gonna be the final result. Yeah. But after this one, how many different kind of cases? Definitely we're gonna have 3 different kind of cases. So currently it is index I, but for the 0-1 knapsack, we need to move to the next. It's gonna be I plus 1. And what about the cost? If we didn't choose anything, so the cost is gonna be itself. Yeah. Now if we want to choose one topping of this current index, yeah, if we can choose one topping, what gonna it be? It's gonna be cost plus the topping cost with this index I. But we can have another decision. We can choose 2 toppings according to the problem. So it's gonna be the topping with I times 2. So this is just according to the problem. Yeah. If we can turn this problem into a 0-1 knapsack problem, definitely it's gonna be easy. Yeah. Normally for a 0-1 knapsack, those 2 branches is enough. But for our problem, we're gonna have at most 2 toppings. So this is why we need to add another branch. Yeah. So normally it's gonna be a binary tree. It is okay. But currently for our DFS, it's gonna be a ternary tree. It means it's gonna have 3 branches, but the problem is gonna be the same. Yeah. So this is the only difference of the problem. We're gonna have another branch of DFS. Now we can check the condition for this I equal to the length of the topping cost. So our condition is that we're gonna check. Yeah. So if yeah, let's just use this cost. So this is our current cost. So we're gonna use the absolute value. So if absolute of the cost minus the target less than the absolute of the self.result. So this is our final result. From beginning, it's gonna be infinity. So if this one minus the target absolute value, if this cost is less than this is just a distance checking because we're gonna use the absolute value. So if the distance is closer, definitely we're gonna update it. So self.result gonna be equal to the cost, and finally we're gonna have a return. Yeah. So this is for one of the conditions. Let's just have a check. Yeah, as we can see, we passed for some testing cases, but the testing cases 4 is not okay because our output is 11. Definitely it's gonna be 9. Yeah, why it is 9? So if we have a base cost of 1, we can choose 8 or 10. So both of them are gonna be okay. But 9 is closer to 10, so this is why we're going to choose 9 instead of 11. But why we return 11? Because we didn't have this kind of the case checking. So the case is that if they're equal. Yeah. So I'm going to add a OR, and I'm going to check if they are equal. So I'm going to copy and paste, and turn is less than to equal. Yeah. So if they are equal, and the cost is less than the target. So this is just for this case. So 8 is less than 9, So currently the cost is 9. So if this 9 is less than 10, so definitely I'm gonna choose 9 instead of this 11. Yeah. So I'm gonna update the result. And finally, I'm gonna have a return. Yeah. So this means if this I equal to the length of the topping cost, definitely I'm gonna have a return. Otherwise, I'm gonna have time limit exceeded. I have to terminate on this branch for the DFS. Yeah, now let me just run it to have a check. Now, as you can see, it works. Yeah, because this one include all the testing cases, and finally, we're gonna have a return. And this is just for 0, 1 knapsack. But for our problem, we're gonna have 3 branches, but it's gonna be the same idea. So this means we're gonna choose nothing. Here, we're gonna choose 1. Here, we're gonna choose 2 for the current index. Now, let me just run it to have a check. As you can see, it works. Now let's analyze a little bit about the time complexity. For here, even we have 3 DFS, this is okay. We're gonna still see it, this is 01. And for here, this is just 01 as well. But for the DFS, let's just check this one. So definitely we're gonna go through with all the base cost. Yeah, from here. So this is a outer for loop. So we're gonna check the length of the base cost. So it's gonna be n. So n gonna be 10, and then we're gonna call this DFS. Yeah. So for this DFS, for each of the time we're gonna use this base, but this base is fixed. It is okay, but we're gonna use this index 0. Yeah. So this means we are having an array, and the array is the topping cost, and it is m. M is less than or equal to 10. This means this array is 10. But for each of the numbers, we're gonna have 3 different decisions. We're gonna have 0, 1, or 2. So this means the final result is gonna be 3 to the power of 10. Yeah, this is for the calculation for the DFS. But here we're gonna have another for loop. So this means it is gonna be 10 times 3 to the power of 10. So this is gonna be the final time complexity. We can see that this is going to be a smaller number. Maybe it is 2 to the power of 20 or so. Yeah, this is just my guess, but I think the time complexity is going to be okay. Basically, it's going to be 10 to the power of 6. Yeah, I think that's all about it. Thank you for watching. See you next time.